So hi everyone, thank you for being here for the third webinar of the TAPAS project. I've tried to send around the link to see the two first webinars. They are on the YouTube channel of TAPAS, so you can also access them through the TAPAS website. And today we will have two presentations, one by Zhengjun and the other one by Wei. So I will let them introduce themselves and the topic that they are presenting. So Zhengjun, you can start. Thank you very much.
Hello everyone, I'm Zhengjun, and this is a presentation for the TAPAS third webinars about my project during my PhD. So thank you all for coming today. And I'm from University of Sheffield, the Span and Age Group in UK. My supervisors are Heidi Christensen and John Bucker. So TAPAS is a training network on automatic processing of pathological speech. My work focused on proposing and developing new techniques for dysarthric speech recognition and evaluating some techniques. So this aims to help people with dysarthria better communicate with others and better interact with machines. So my topic I'm going to present today is continuous speech recognition for people with dysarthria. And here is the outline of today's presentation, which will include the introduction, the objective, and I will introduce the research questions and methodology together, so including 3 of my work. And finally, I will introduce the contribution and future work. So to start, I will give you a brief background on dysarthric speech. So dysarthria is a speech disorder, and which is the most commonly acquired speech disorder caused by disruption in neuromotor interface. So stroke, cerebral palsy, and like Parkinson's disease are the most prevalent causes of dysarthric speech in the UK. This neurological damage causes the uncoordination of muscles used for speaking. So this impacts the physical production of speech. And therefore, people with dysarthria often have poor motor control of their speech articulators. So producing like speech characterized as heavily slurred or having the slower speaking rate or abnormal pauses, false starts, and repetitions. So I'll briefly show you 2 examples taken from the Togo corpus of dysarthric speech. I want to first show you the severity case. Yeah, and then I will show you speech from a mild speaker, but like say the same urgency. Yes, as we can heard, the dysarthric speech, especially.
I think you didn't share the audio. I couldn't listen and listen.
You couldn't hear it?
No, I think you did. When you share the Zoom, you need to click down. There is an option for sharing the audio. Probably you didn't do that.
Okay, let me see if I can new share the sound. Okay. Oh, this. And can you hear now?
Not yet, but you didn't stop sharing. Maybe you have to stop sharing and share again.
Okay, yes, you share.
And choose down, there is an option of audio sharing or something like that.
Yes, makes sense. And now?
This was easy for us.
Yes, perfect.
Oh, Cool. Oh, sorry. Yeah, so we just start from the severe case. I will show you this first one. Yeah, and the mild case say the same urgence.
This was easy for us.
Yeah, so like as you heard, the dysarthric speech, especially in the severe case, can be very difficult to understand for people who are not familiar with them, like their close family and friends. And this reduced intelligibility of dysarthric speech can cause problems in human-human communication, which in turn will affect the social interaction or employment, and even affect their education. And moreover, the people with dysarthria often have physical disabilities, such as those associated with stroke and cerebral palsy. They often have more limited or involuntary body movements. So as a result, they may experience difficulty carrying out some simple daily tasks, such as using the handles or switches. It's also very difficult for them to interact with some physical devices such as keyboards and touch screens. So these problems demonstrate increasing need to establish the systems that can facilitate the human-human communication and human-machine high-performance interaction for people with dysarthria, which may improve their well-being and independence. Yeah, and one of the solutions is to use the voice-driven assistant technology. Automatic speech recognition technology is today's voice-enabled interfaces by converting the spoken utterances into the text transcriptions. So this enables us to use our voice with the AI technologies, such as the remote controls, whether it is in our homes, cars, offices, or elsewhere. And in this case, the speech provides an attractive interface for using the hand-free human-machine interaction. This can replace the traditional physical interface elements like keys, knobs, and handles. So ASR technology has potential to help people with dysarthria carry out the simple daily tasks, and like with a more natural interaction with machines without the need to move their bodies. And in addition, if we have a high performance ASR system, this can also provide an accuracy text transcription for the dysarthric urgencies, which help people with dysarthria better communicate with others. Eventually, so this technology would greatly improve the quality of life of people with dysarthria. However, the current available commercial ASR systems do not work reliably for dysarthric speech, because the mainstream ASR systems are usually trained on the large amount of like typical speech and fail to capture the specific characteristic of a person's dysarthria. The ASR's performance on dysarthric speech is considerably lower than that achieved for the typical speech. Here are some challenges. So, for example, the large mismatch between the typical and dysarthric speech, or the significant variability either the interspeaker or intraspeaker. And data scarcity is also a main issue of this task. So these are the three main challenges. It's also noticeable that most of the previous studies on this task have focused on the isolated word. Although a single word recognition system can be a great help for people with dysarthria, but it wouldn't be adequate for to cover most of their needs. Instead, the continuous speech, so like phrases or sentences, these are much more natural to use. So like the typical speech, the ASR technology on the dysarthric speech should also progress from the isolated word to the continuous speech. However, like the continuous speech case is more challenging than the isolated word task, because first, the continuous dysarthric speech has more variability, and because when people saying the multiple words, it's hard to move their articulators from one position to another position. So people with dysarthria might have like more difficulty to do this. And secondly, decoding is particularly difficult for continuous dysarthric speech, where there's increased uncertainty. When we speak like multiple words, it's also very challenging to locate the word boundaries in a sentence, and the effects of co-articulations is also more challenging in this case. And finally, compared with the isolated word, there is much less continuous dysarthric speech data available, so which is insufficient to train an adequate model application applicable for this continuous dysarthric speech. Yeah. And then this is the objective of my project. The purpose of this research is to explore various approaches to build the reliable and high-performance ASR system for continuous dysarthric speech. And this will improve the ability of people with dysarthria to communicate in a more natural manner with both human and machines. So finally, this will increase their social participation and improve their independence in life. So before I start introducing the research questions and methodology, I'd like to introduce the data I used in my project. So Toggle, this is called Toggle. Toggle is one of the few available and widely used dysarthric speech database. It has 15 speakers, so 8 of the speakers have dysarthria ranging from different severity levels, from the mild to severe. And while the other 7 are the typical speakers, and the dysarthric speakers has 5 males and 3 females. So typical speakers includes 4 males and 3 females. What makes this dataset attractive is that it contains aligned acoustic and articulatory recordings. So this can help us to build some multimodal architectures, and it's because it's contain both the isolated words and sentences. So this is the most suitable database to explore the methodologies for continuous dysarthric speech. Okay, let's move on to my work, and I will introduce in 3 of my work. So the first one is out-of-domain language modeling. To progress this task from the isolated word to continuous speech, it's important to identify and consider the difference between these 2 tasks. So because most previous studies have focused on the isolated words using this closed set vocabularies, where the training and test vocabularies were the same. However, this is not applicable to how the continuous speech ASR system should be evaluated. When it comes to this task, a language model is needed, and the language model greatly affects the results. So because this continuous dysarthric speech recognition is a low resource task, and the collected corpora normally have limited numbers of sentences with limited vocabulary sizes. So this leads to problem when using a language model only trained on the limited prompts within such dysarthric datasets. So during the pilot study, we observed that most of the datasets are designed for ASR tasks, but instead for purposes such as speech assessment. This will cause the problem that there is much overlapped prompts across speakers. And in this case, the training and test sets are usually non-disjoint. This will lead to the unfair decoding process. And in addition, the limited vocabulary size usually results in a large auto-vocabulary rate. So this will also influence the recognition performance. So the previous ASR evaluations have often neglected this problem, so using the unfair language models. And this leads us to the question, what's an appropriate evaluation framework for the continuous Dysarthric speech recognition given the current limitation? So the first work of mine is to build a baseline with a fair evaluation system. So proposed a language model trained on an out-of-domain data, which called Libre speech data for the current state of the art for Dysarthric read speech ASR. And this framework has been published as an ICAST conference paper. So in this work, we evaluated the ASR system using the language model used in the previous toggle-based studies. And we also try like different out-of-domain language models from the Libre speech by limit the by changing the different vocabulary sizes, and we build like unigram language model for the word task and trigram language model for the sentence task. So in conclusion, this work let us know that the Libre speech language model have power but fewer performance on this task, and by reporting the results on the individual task, so we found that these tasks are different, and in general, the largest vocabulary size, the lowest word error rate. And so this out-of-domain language model will be used in my subsequent work. Yes, and the second work, so this is using a novel speech representation learning framework. The feature extraction is the first step in the speech processing. It carries information, like very important information that will be learned by the following neural networks. And nowadays, with the popularity of the deep learning approaches, and so the speech representations are using these deep learning methods to learn like higher level representations. However, because the Dysarthric ASR is a low resource system, so this leads us to question that what is the good way to leverage the typical speech, which is out of domain, to learn more robust representations for continuous Dysarthric speech. So this work I focus on using the state-of-the-art acoustic models, which called LIGRU layers, and also explore like different speech representation extraction strategy. Yeah, this is the architecture of this work. So in the left, that's a feature extractor, and in the right, it's a speech recognizer. So in this work, I proposed to use the feature called autoencoder bottleneck features, and using the multitask optimization schemes. So the first one is a joint learning the feature extractor and the speech recognizer by adding this MSE loss and the cross entropy loss together. In this way, the speech recognizer, like the phoneme classification, these targets can guide the feature extractor to extract features that is more like task beneficial. Yeah, in addition, I also proposed to use the modal phone regularization, and this one can prevent overfitting of this speech recognizer. And the results found that augmenting this feature can reduce word error rate, and using the multitask optimization task schemes such as monophone regularization and joint optimization can also reduce word error rate. Yeah. The last work I did is the multimodal acoustic articulatory speech recognition system. So the research question is that how can articulatory information be incorporated effectively to build the multimodal systems for this task? And the motivation is that because of the high variation of Dysarthric speech, using acoustic information is not enough to capture the clue or the characteristic of the Dysarthric speech, but like by incorporating the additional information might help in this case, and that's why we lead to this research question. And in this work, we just combine these two features, and we tried like different methodologies and different fusion levels to fuse these two features. Yeah, so because of time limitation, I will just briefly introduce the motivation. And compared with the acoustic information, articulatory information can capture the movement of speakers' articulators and can complement the acoustic features because it's simpler to model and is more noise robust and less speaker variant. It can also help model the co-articulation variabilities. That's why we think articulatory information can help with this task. However, there are three current research gaps in this task. The first one is the real articulatory data is actually underexplored. The previous studies was used, like most of the previous studies, they used the synthetic Dysarthric articulatory representation, which is learned by the mapping from the acoustic and articulatory. And this mapping usually learned from the typical speech. So yeah, that's why we think because of the mismatch, it cannot represent the Dysarthric speech while. And the last is the optimal fusion level is underexplored. So this is the architecture of my third work. By doing some pre-processing, like using the filter to remove the measurement noise and downsampling the signals and choose like the optimal channel, we got this articulatory features, and by different neural networks, we combine these two features, we fuse these two features at different levels. And we found that, so this is the different concatenation schemes. The first one is without CNN, just by simply combine them. And the second is adding some CNN layers. And the third is concatenate them in the medium level, and finally just concatenate them in the more higher level, so the level before the MLP but after the LHGRU layer. And the results show that by a directly fuse these two features can have like 1.9% word error rate reduction. And by fusion scheme, so the best fusion scheme is concat 2, which is at the medium level, which can have further improvement. And we also found that so the when we want to fuse two different features, the level should be high enough to avoid overfitting, to be low enough to avoid overfitting, but high enough to give like space to process like each streams. And yeah, so these are the three works of mine. The summary is, so in my project, I developed benchmark for the automatic Dysarthric speech recognition. I have explored different language models, out-of-domain language model, and using different acoustic modeling, learn like different speech representations. I tackle problems by utilizing the out-of-domain data and using transfer learning strategy. Also, finally, I use this multimodal acoustic modeling scheme architecture. Yes, and what could be improved in my future work is I will get more data to train like more robust system and more generalized system. Maybe extend the multimodal acoustic articulatory speech recognition systems using other like advanced frameworks. Also considering the voice conversion or raw waveform or modeling to do this task. And maybe someday I can integrate my work in the softwares or the wearable devices. And thank you for your attention.
Thank you very much. Are there any questions? I have a question on your contribution number 2, because on your slides you you just mentioned at the end that it's transfer learning, is it? But I didn't see in your architecture like, is it like you are only test on Torgo, or is it a pre-training on LibreSpeech, or I didn't get that point.
Yes, so the feature extractor is pre-trained on the LibreSpeech, and then I use transfer learning just by fine-tuning the last two layers of this autoencoder. And yes, so this is transfer learning. And also we extract toggle features from here, and then for the speech recognizer, we just use the toggle. Yeah, we didn't use LibreSpeech for speech recognizer in this task.
Okay. Hank, do you want to ask her a question?
Yes, very briefly on your third experiment, and it's where you say the articulatory work, the extraction that you did. In the table, I saw that you something like lip. Did you only use the lip articulation or also tongue articulation feature?
Yes, so sorry. So in this work, because here we have a channel processing, this means we choose like the best task beneficial feature. We tried different like components or them together. So you can see in this figure, yeah, we have like the sensors attached attached to the tongues or the lips. We tried like different components of them, and we found we use this lip information. And I also, but I mentioned in my paper that I like use this Euclidean distance instead of using the raw information, and this can give us the best result. Yeah.
Okay, thank you.
No problem.
Thank you, Zhengjun. So let me introduce our next speaker if there is no other questions. I didn't see any hand.
Yeah, thank you. Thank you for your attention. Yeah.
And if you want to ask her other questions, there is also her email on the TAPAS website. So I don't know, but I think she will be happy to answer questions on emails.
Yeah, I'm very happy. Yeah.
And yeah, so Wei, if you want to share your slides.
Yes. Does Zhengjun needs to stop? I guess so.
Yeah, maybe she has to stop. Yeah, great.
Wait a minute. Screen. Can you see it?
Yes.
Should be the full screen, right? Okay. 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 So hi everyone. My name is Xue Wei. Wei is my first name. Currently, I'm studying my PhD at the Harvard University in Center for Language and Speech Technology. I'm founded by the TAPAS project, of course. And as Zhengjun introduced, our TAPAS project is mainly focused on Dysarthria or pathological speech. And today, what I'm going to introduce about my own research is called Developing Valid Measures of Pathological Speech Intelligibility, Human Ratings, and Automatic Scores, which mainly focus on the study of speech intelligibility for Dysarthric speech. My supervisors are Helmer Streich, Katja Kujani, and Roland van Hout. So as you can see from this title here, there are some terms you just heard from Zhengjun and maybe also previous presentations, But let me introduce more in detail that what is basically pathological speech is and what is speech intelligibility and their relationships. So pathological speech usually refers to speech impairments that can be caused by motor speech disorders, including dysarthria. And dysarthric speech is basically one of my research objects. And dysarthria is normally caused by neurological speech disorders such as Parkinson's disease, stroke, dementia, etc. And furthermore, dysarthria can result in abnormalities in breathing, phonatory, resonator, articulator, or prosodic aspects. And these aspects are relevant for producing speech, and therefore the abnormalities in them can result in the impaired speech. And patients with dysarthria normally suffer from
Am I the only one not to hear her anymore?
No.
Okay.
Sorry for that. I think I was disconnected for a moment. So where were you, by the way? Where I just left or left? What information you missed?
I think you can start again this slide if you don't mind.
Oh, this slide. Okay,
Yeah.
no problem. Okay. So start again that pathological speech usually refers to speech impairments that can be caused by motor speech disorders, including dysarthria. And dysarthric speech is one of my research objects. In more detail, dysarthria is normally caused by neurological disease such as Parkinson's, stroke, dementia, etc. Furthermore, dysarthria can result in abnormalities in breathing, in phonatory, resonator, articulatory, or prosodic aspects. So these aspects are relevant for producing speech, and therefore the abnormalities in them can result in impaired speech. And patients with dysarthria normally, because of this, suffer from losing control of muscles in their system, and thus cannot produce speech signal as well as healthy speakers. And because of this, these speakers gradually lose contact with their friends, families, and even society. So to help them, it is possible to take intensive speech therapy given by speech language therapists to slow down the progress of dysarthria. And to monitor the effectiveness of speech therapy and to identify the degree of speech impairment, we can use a notion called speech intelligibility. However, speech intelligibility has many different definitions in different studies. While in my research, I generally adopted a pretty neutral one, that is, speech intelligibility refers to how well a speaker's acoustic signal can be accurately recovered by a listener, which was proposed by Houston in 2007. Intelligibility is a pretty complex construct as it can be influenced by the above mentioned abnormalities. So a point of concern here is that according to the definition of speech intelligibility you just saw, it is pretty obvious how to measure the intelligibility. That is, it seems that it is not possible to measure intelligibility without involving any human listeners. Thus, one approach of measuring intelligibility is this subjective procedure by involving the human listeners. Briefly, we generally recruit a group of listeners to give assessment of intelligibility through different methods, such as visual analog scale, which is a scale placed either vertically or horizontally, ranging from like 0 to 100, where 0 refers to not intelligible and 100 refers to intelligible. The listeners are asked to set a number on the scale that represents how intelligible they think the speech that they just heard is. Another commonly used method is to collect orthographic transcriptions for recordings of Dysarthric speech, and then calculate measures from the transcription, such as accuracy of words, word error rate, etc. And there are also many other different methods. In addition, these methods can be applied on recordings of different speech materials, such as sentences, words, passages or phonemes, graphemes, etc. And then the intelligibility can be studied at different granularity levels, depending on the unit of study, such as if you focus on utterance or word or phoneme level, you study intelligibility at that level. This subjective procedure generates what we call the human scores. As you can imagine, such approach is very time-consuming and costly. Thus, clinicians and researchers are looking for objective procedures which can automatically generate speech intelligibility measures by using speech technologies such as automatic speech recognition you just heard from Zhengjun's presentation. We can also calculate acoustic phonetic features directly from the Dysarthric speech and explore their relation with the human scores collected through the above subjective procedure. And this objective procedure produce what we call the automatic scores. So my research topic is about developing valid measures of intelligibility through both procedures. And I'm going to introduce 2 studies for each procedure and make conclusions from them. Specifically, to study the human scores, I conducted the listening experiments and analyzed intelligibility measures obtained through different methods for both the Flemish Dutch and Netherlandic Dutch. By the way, the Flemish Dutch refers to a Dutch variety that's used in Flanders in Belgium. And to study the automatic scores, what I present in this presentation is mainly about acoustic phonetic features. I will introduce 2 studies, one for predicting speech type, whether an utterance is Dysarthric or healthy speech, and the other one for predicting intelligibility at phoneme level. As I just mentioned, to collect the human scores, I conducted a listening experiment about Flemish Dutch. The experiments were conducted when I did my secondment in the University Hospital of Antwerp, abbreviated UZA, in Belgium. And thanks to the help of Professor Gwen van Nuffelen, Professor Mark de Borg, and another TAPAS student, Viviana Mendoza, I managed to collect the data during the corona pandemic. The results have been published in the Proceedings of Interspeech 2020 and in the Journal of Clinical Linguistics and Phonetics. While here in this presentation, I want to describe 2 of the experiments in more detail, namely the sentence experiment and the word experiment. For speakers and speech materials involved in these 2 experiments, specifically, the sentence experiment covered the 36 speakers, consisting of both the healthy speakers and the Dysarthric speakers at different severity level. You may just know a little bit about the severity level in Zhengjun's presentation, where you heard the mildly Dysarthric speech and severe Dysarthric speech. So these speakers read 4 meaningful sentences selected from a phonetically balanced text, which is also commonly used in clinical trials called Papa and Malus. In English is Papa and Malus. The word experiment covered the half of the speakers of those in the sentence experiment. And these speakers also consisted of healthy speakers and dysarthric speakers with varying at different severity levels. These speakers read the 3 consonant vowel consonant word list that are selected from a standardized Dutch intelligibility assessment task. The speakers and the recordings used for assessing intelligibility were all selected or extracted from the TAPAS dataset. To collect the human scores, I used the 2 methods, the visual analog scale, FAS, and orthographic transcriptions. And for orthographic transcriptions, I applied novel form of transcription called AW trans, short of all word transcription, which allows all kinds of words, including persona words. And I compare that to the commonly used one, what called EW transform, short of existing word transcription, which allows only existing words. You may see that I only applied AW trans in the word experiment. This is because the word list contains persona words, so we thought it's not reasonable to apply the EW transform. Then the accuracy of words was extracted from these orthographic transcriptions. And we also recruited 5 experts to participate in both experiments. So these experts were speech language pathologists and had very rich experience in assessing intelligibility and giving therapy to dysarthric speakers. To explore the difference in the human scores, I also analyzed the listening experiment of Netherlandic Dutch. And this experiment was conducted by a master's student at Harvard University at that time. And the related results were published in the Proceedings of Interspeech 2021. So this experiment involved 18 speakers, also again consisting of healthy and dysarthric speakers. And this speaker read the same 4 sentences as you see in the sentence experiment, and also another 2 word lists, each having 3 words. Again, FAS and orthographic transcription in the EW transform were applied. And for the listeners, we recruited 11 speech language pathologists to evaluate the intelligibility. However, although these listeners were therapists, they had very limited experience with dysarthric speech. So they can be seen as naive listeners to a certain extent. Since we're collecting intelligibility measures from human listeners, it is always necessary to check the reliability and validity of the measures. In this slide, I first show you the inter-rater reliability in this table. As you can observe that the reliability value for FAS in all 3 experiments are higher than 0.90. So these results indicate that FAS is consistently reliable in different contexts regarding speech materials and rater types. For the accuracy of words extracted from the orthographic transcription, the reliability values in the new AW transform is much higher than the one in the EW transform, especially when the readers are familiar with the speech material and in the sentence experiment. So these results suggest that AW trans seems to provide more reliable intelligibility measures than the EW transform. Moreover, the reliability of the accuracy of words in the experiment for the Netherlandic Dutch is very low, that's with only 0.47. In fact, we analyzed the distribution of the accuracy of word scores. The rather low reliability in this experiment was due to the very few variations in the scores. As you can see from this figure, that many utterances received intelligibility of 100 because the listeners transcribed all words perfectly. On the one hand, it might be that the speakers were generally mildly Dysarthric in the Netherlandic Dutch. On the other hand, it may be that when the readers were so familiar with the speech materials, they depended much on the contextual information and their memories, especially when they are not experts. Thus, it seems that the contextual information in the meaningful sentences might be limited to a certain extent by using the AW transform compared to the EW transform. Following the analysis of reliability, we also analyze construct and concurrent validity of the measures. Here I present you only the construct validity, which was studied by computing the correlation between the two measures in each experiment and also across experiments. As you can see from the table that fuzz and accuracy of words from both forms of transcriptions showed very strong correlations. In the experiment for Flemish Dutch, these results indicate that these measures seem to refer to similar construct of intelligibility when the readers are experts. However, the correlation for the Netherlandic Dutch experiment was only moderate. This indicates that these measures refer to different constructs of intelligibility when the readers are not experts. Further, the correlation for each measure between two experiments were always below 0.90. So these results seem to show that perhaps that different constructs of intelligibility are measured in different speech materials. So from the results I just presented, we can conclude that readers type, whether they are expert or not expert, with assessing Dysarthric speech can influence the reliability of speech intelligibility measures, especially for the transcription-based measure. Further, it seems that measures of intelligibility are related to different constructs of intelligibility when they are obtained through like different measurement methods, such as fuzz or orthographic transcription, and using different speech materials, such as in the sentences or on the word list, as well as when they are at different granularity levels, whether study a sentence or word, etc. Again, this shows that intelligibility is a complex construct. Thus, it is necessary to involve different speech materials and collect measures of intelligibility at different levels. Recall that for automatic scores, as I explained before, it is possible to use ASR or acoustic phonetic features. While in this presentation, I present two studies related to acoustic phonetic features. The first one is to predict the speech type, namely whether speech is healthy or dysarthric. Later, we'll see the second one for predicting intelligibility at the phoneme level. So in this study, we want to explore to what extent automatic features can contribute to speech type classification and provide the basics for more objective evaluations of intelligibility. We used the data of the Netherlandic Dutch you just saw, and aside from these human scores, we also calculate several phonetic features that are related to intelligibility and can contribute to distinguishing Dysarthric speech from healthy speech. Then we put these features as predictors in a stepwise logistic regression to predict whether an utterance is Dysarthric or healthy. The predicted speech type probability at the utterance level were aggregated over the utterance as the overall acoustic phonetic probability index, abbreviated as API. So for the accuracy of classification, we observed a mean classification accuracy of 79%, with 50% for healthy speech and 88% for Dysarthric speech. We also studied the correlation between the API and human scores at speaker level, as shown in the two figures here, where the y-axis is the API and the x-axis is the human scores. we can see that the correlation between API and fuzz is significantly moderate, whereas there's no correlation between the API and the accuracy of words. So these results indicate that the intelligibility measures and the API based on the acoustic phonetic features are partly complementary to each other. In other words, it seems that intelligibility measures assigned by human readers and acoustic phonetic features relate to different constructs of intelligibility. So my second study is to predict intelligibility at the phoneme level. This study has been published in the Proceeding of Slate workshop in 2019. In this study, we explored to what extent these automatically calculated features are related to intelligibility scores of pathological and healthy speech. So this study used a different data set and feature set that from the previous study. Specifically, we used the TAPAS data set with more speakers. We studied 2 speech materials, again, the full text of Papa and Malus, and also, again, the 3 CVC word list from the DIA task. And speakers were selected based on whether they have the recordings for both speech materials. In the end, we found 49 dysarthric speakers and 81 healthy speakers. The human scores we used were phoneme intelligibility obtained through the DIA task. It is calculated at the percentage of correctly transcribed target phonemes over 3 word lists for each speaker. For the acoustic phonetic features, we mainly study a standardized set of features called EG maps. It contains low-level descriptors that are related to, for example, frequency, energy, loudness, pitch, etc., as well as functional of some of these descriptors. In total, it contains 88 features, and these features can be easily extracted by using the open source software called OpenSmile. Moreover, we applied a Pratt script to calculate a set of speech rate related features by automatically detecting syllable nuclei without using segmentations. These features are related to speech rate, articulation rate, to number of syllables, etc. We use this complementary feature set because it may identify additional parameters related to intelligibility. And in order to investigate the relation between speech intelligibility and acoustic features, we applied the stepwise linear multiple regression. In detail, we will first provide a 1-round regression to predict the phoneme intelligibility by using the EG maps features. And then we further apply the second round linear regression by using the EG maps features together with the speech rate features to predict the residual in the first round linear regression models. This was aimed to investigate whether the speech rate related features can complement the EG maps features for better predicting the intelligibility scores. So this table here represents a multiple R-squared score for the final linear regression models. This score represents the proportion of the variance of the dependent variable that could be explained by the independent variable. So the higher the score, the better the acoustic phonetic features can explain the variance of the dependent variables, such as what we used, the phoneme intelligibility. As you can see, the multiple R-squared score are higher for the dysarthric speech on the isolated words, so the DIA task, than using the running speech in the PM text. Whereas healthy speech showed similar and relatively low scores in both speech materials. This indicates that phoneme intelligibility for dysarthric and healthy speech seem to rely on different acoustic features. Moreover, for dysarthric speech, if we combine with the residual and fitted values plots in the first round of linear regression, we can see that the model for dysarthric speech achieves higher of the larger residuals values on the PM text. So these results are not surprising since the phoneme intelligibility scores were calculated based on the isolated word in the DIA task. And it seems that it does not generalize to the running speech in the PM text. And it could be the case that phoneme intelligibility only reviews one aspect of general speech intelligibility for Dysarthric speech. In the case of running speech, the PM text, including the speech rate related features, seem to help improve the performance. And this indicates that speech rate is an important exploratory factor that could be employed to complement the EGMAPS feature set. Overall, we can conclude that to predict intelligibility or to classify speech type, it is necessary to use acoustic phonectic features that are relevant for that specific speech material, since they perform differently in different materials. And also, such manually extracted features do not seem to be enough for explaining the variance of intelligibility. So using neural networks, such as the convolutional neural networks to learn the features directly from the speech may be a future direction. In general, combining both the study of subjective and objective procedures, it seems that it is necessary to use different subjective procedures to evaluate speech intelligibility, and it is necessary to study the above human scores in relation to relevant but different features in different contexts. And once we have found the relevant speech, the features or the objective procedures, it will be possible to automatically generate the intelligibility assessment. Thank you for your listening. If you have any questions, feel free to ask.
Thank you. Are there any questions? I have one. I was wondering,
Yes.
when the therapists, the experts are told to assess the intelligibility, do they have only the, what exactly are they told to do? Are they just told like
Instruction,
or do they have like smaller tasks to do to bring them, you know, to be sure that they all understand the same by the word intelligibility?
I think we don't ask for that, or we didn't check whether they have the same understanding of the term speech intelligibility. But this can be shown with a high iterative reliability, right? So because they perform similarly on when they measure the intelligibility. So that can in turn prove that, oh, they seem to have the similar understanding of intelligibility. And this, you can also see that when the experts who have very rich experience with speech intelligibility assessment, you see the higher iterative reliability. Whereas the people, when they have very less experience with Dysarthric speech or with speech intelligibility, you have seen that the reliability is very low. It's below 0.50. So that shows that, okay, it seems that naive listeners, they have different understanding of the notion of speech intelligibility. That's why in many previous studies, when the naive listeners are used as the participants, much more people should be recruited compared to the number of experts as listeners.
Yeah.
Yeah.
Okay.
So that's why intelligibility is pretty complex. Yeah.
Yeah, it was like one of the study that Timothy did, like to understand what was intelligibility and severity, and quality of speech, stuff like that. They are all the same, but not quite. So sometimes you have to be sure that everyone understands the same. It depends also on the topic you are involved in. It's not the same for like computer scientists. It's not the same for phoneticians, etc. So
indeed, yeah. So I think I'm more focused on the speech language pathologist aspects because the original target was to like give guidance for assessing speech intelligibility that they can use and share the results between their colleagues, right? So patients go to one hospital and then another hospital, they can share the results because they have the same agreement on the, for example, the notion of intelligibility or how they are measured. Yeah.
are there any other questions for Wei?
Can I ask a question?
Yes.
Like you mentioned, like you maybe do the assessment by using directly from by using the raw waveform. Is that what you mean?
By using, sorry, I didn't hear clearly.
The audio or the raw waveform?
Yeah, from the recording.
From the recording. Okay. So
yes.
Has someone done this, or like no one have done this, or if no, like why people don't do that? Like currently, is there any like challenges?
You mean learn the speech representations from the speech, or?
What you just mentioned this in your future work. I mean, this is like.
You mean that it seems like the manually extracted features is not enough, that maybe use neural networks, something like that? That's what you mean?
Okay. Maybe I heard something. Yeah, if it's representation. Okay, yeah. Do you use this representation for the classifications?
I didn't use it. I mainly focus on the acoustic phonetic features because many clinicians, they study this. Like they use PRAT, that's what they can use. Like ASR or other speech technologies may be too difficult for them. So I first study whether they have relations with speech intelligibility, but I also found that you need to select the features very carefully, and that's pretty hard to do, right? So instead of doing that, maybe like learning the features, like using the neural networks directly from the speech is more easier. And if there's some like packages that they can just simply to click run and get the results, that would be wonderful, right?
Yeah, thank you.
So there is also a question from Abdesalem.
Yes.
Yes. Can you hear me?
Yeah.
Okay, good. Hey, so your work is kind of related to the thing I'm working on. It's just we are going different ways about it. But I just have a question about the intelligibility part. I think it's somewhere about slide 11, if I remember correctly, or anyway, about the results. So you mentioned that you use the corpus database for the intelligibility.
Yeah.
And I just would like to know, how did you validate the results you got? Because you've just shown the scores for corpus database, but then I'm not sure. I'm not sure if I missed this part. So how did you validate those results? If you use any database or any other system to validate?
What do you mean by validate? Because I use the recordings and present to, well, if you mean slide 11, actually I didn't do any human score collections. So these are the data in the corpus database, right? And these are the other things I did in my research. But the phoneme intelligibility through the DIA task has been published in the paper that it had very high inter-rater and intra-rater reliability. So that, to a certain extent, you can trust the scores.
Okay. Okay.
Yeah.
Okay, so thank you, everyone. So I will send around the link again for the recordings, and so see you next week for the first edition. And yes, that was great to have you today, and see you next week.
Thank you. Bye.
Thank
Bye.
you. Bye bye.
Bye,
See
everyone.
you next week.
Bye. See you next week.
See you. Bye.